Good afternoon, everyone. I would first like to thank the organizers, Ronojoy, Ronjini and Pramod for giving us this opportunity to share our work. So today we will be talking about what we are very passionate about, so soft oxometalates. I'll talk about what they are and where are we with the soft oxometalates, and then later after this talk I think Oyon will talk a little bit about a detailed aspect of one of the SOM mediated phenomena. So what are these and what do we mean by these soft oxometalates? So let us explore it a bit more in detail. Yeah. Okay. Yeah. So now this short clip, movie or this short snippet shows our basic perspective on what we mean by these soft oxometalates. Now you see, this has been an ongoing effort. So I am from the background of chemistry. So in chemistry, people like Berzelius, Scheele, they have been working on clusters based on metal oxides that have charges, and that used to show very fascinating chemistry but was not able to be understood. So they couldn't understand it. So for instance, the classic example of this chemistry comes from molybdenum blue, the mystery of molybdenum blue. What is that? So in undergraduate experiment, people do this experiment. So you have a molybdenum salt, let's say. You add some acid to it, you add a reducing agent, and then you get a colloid, a blue colloid. That remained enigmatic over a long period of time till the clusters were synthesized, crystallized, and now we understand that many of these behavior of these materials are nothing but soft states of metal oxide based clusters that are charged. These are nothing but the soft oxometalates. So we have defined this paradigm where you have these metal oxide based clusters which are soft, and thus show the potential of showing different possibilities like phase transition, and we have exploited in patterning and so on, and catalysis and so on and so forth. So this is a state that we have defined, and this is what we mean by the soft oxometalates. Now I will show you, for instance, this video is that of a freezing soap bubble. So this is a soap bubble and this is freezing. Now what it represents? It actually represents what we can do with these soft oxometalates. Now what do we mean? Here, for instance, the soap molecules, the surfactant molecules, they are nothing but the oxometalates. And you can, for instance, change shape. It's a cooling phenomena, so we were showing that we are cooling it down, and then you see that you can crystallize it. So basically you can induce shape transition. So if you would see this one again, for instance, you can see like, you know, you can just press a soap bubble, you can induce a deformation in it. Now you can we induce deformation, we can induce shape changes in the soft oxometalates by using light, for instance. So I'll talk about it. We can induce phase transition. Instead of cooling it down, we do it again with light. We will talk about it. So these are the phenomena, and of course why we do it, one of the main reasons we do it is because to apply them in catalysis. So that is the fascinating aspect of these soft oxometalates. And then we were lucky, for instance, last year I guess, I had the opportunity to meet Ronojoy and we had a nice discussion, and then he attracted our attention that can you render these soft materials active? So we will talk about them, and these are in the future directions. So we are now able to render these materials, these soft oxometalates, mobile. So we can make them active, we can make them move without any external applied field but by simple chemistry. That is what we are able to do. So we will show them, and we will also show them because our chemistry or our materials are based on water and light. These are the two things with which we explore complexity, and with this we have now ventured upon the aspect of achieving artificial photosynthesis. So what we have done, we have used carbon dioxide and water, and we are making now carbon monoxide or formic acid instead of glucose. Of course, you don't want glucose, right? Because the economy, the fuel of the economy is carbon monoxide, which is an upstream product. That means you can make a lot of products from it, or formic acid, for instance, with which we can make fuel cells out of it. So we are making it, and the byproduct is oxygen, which is purely environmental friendly, and we don't use any other materials. So this is the overarching theme of my talk, and I'll then be glad to have interactions, and I'm open for collaboration and opportunities. So this is more or less, yes.
What do you mean by soft here again?
Yes, it is the state. So basically what we mean is it is in the liquid state. So it can also be called, for example, liquid oxometalate, right? So it is the state. It is basically, so basically what we mean by that is that you are in the liquid state or the soft state, and then if you go into the crystalline state, then because they are charged, so you cannot call them metal oxides, but they are oxometalates. And because you have usually polynuclearity, so that's why they are polyoxometalates. So that will be the crystalline regime. And we are dealing primarily with the liquid regime. So they might also be called LOMs, for example, liquid oxometalates, or soft oxometalates in that sense, right? So yeah, so now we will, so this is more or less the overview. So first, thanks Guru for this question. So I'll explain a bit more in detail. So what we mean by this state. So basically it is the soft state of metal oxides that flows. It must have a supramolecular connectivity in the condensed phase. So in the dispersed phase, it should have supramolecular connectivity, and it must have at least two phases. So one is the dispersed phase, and the other one is the dispersing medium. So the continuous phase is the solvent, and in most of our cases what we are exploring is water. We are sticking to water because it's a green solvent. We are not venturing into other solvents, so that is intentional, but one can explore other solvents like DMSO, acetonitrile, and so on and so forth. But we are primarily sticking to the solvent, that is water. And yeah, and what we want to say is that this state is actually beyond the crystalline polyoxometalate. So basically if you imagine a density continuum, a number density continuum, in the very low density regime you have the gaseous phases, which is like a dilute solution. Then you have the liquid or the soft phases where you have interaction parameters, where you see these certain aggregates. And then at the high density regime or at the high number density regime, you have the crystalline polyoxometalate state. And what is the other aspect of interest in the soft state is, for instance, if you look at it, we are in a way liquids, right? We have, of course, we are not restricted in some way by the crystalline periodicity. For instance, if we have crystallinity, we have problems like the aging disorders. Like people say that protein doesn't want to crystallize. Of course protein doesn't want to crystallize, because if protein starts crystallizing, we start having pains in our joints. So what do I mean by that? Why it is an opportunity for us, or why we are interested in the soft state? Because in the soft state we can explore the structural manifold that is free of five-fold symmetry. Because if you are in the crystalline regime, if you are in the solid state regime, then you are limited by the five-fold limitation of the space group, five-fold symmetry of the space group. So that is what excites us to explore the liquid regime or the soft oxometalate regime. Now people are picking it up. We had cover pages. We are also doing a special issue. Anyway, so that means it's exciting, and we are very encouraged by the fact that slowly this nomenclature is now being picked up by the community. So now I will talk about the first aspect is the catalysis. It's the photocatalysis. So what we did. So for example, we started with a gold salt. Now a gold 3. Now what we did is gold 3 can be easily reduced, and it is photosensitive, it is photoactive. So what we did, we started with an oxometalate that is molybdenum 132. It has reduced molybdenum 5 centers. We could reduce gold 3 to gold 0 and have molybdenum capping it. Why we did that? Because this way we have generated a photoactive center. We of course monitored its formation from UV-Vis and from Raman spectroscopy, and we found that we are getting this type of anisotropic gold particles coronated with the oxometalates, which could be potential catalysts because they are photoactive. Then we used these ones as a catalyst and loaded styrene into the system. Now, loading styrene into the system, we could get monodisperse polystyrenes without any problem. So, what was happening is you have the oxometalate or the SOMS or the soft oxometalates, they get into the photoexcited state, they then induce an electron transfer and thereby induce a cascade polymerization reaction in styrene, thereby making polystyrenes. So, this was more or less an effect that was nice, but it required more exploration. So, we thought that can we explore more of this photopolymerization. So, we became more direct. This was gold assisted. So, then we thought can we do it with yes.
What was the polydispersity in the?
This was very low. This was within 1%, was rather low, was not very. Yeah. So, this is this one. This is a new journal, Journal of Molecular Engineering Materials, and volume 2, and yeah, this is the page number, and this is this. Yeah. So, then we thought, for instance, like can we now get rid of the gold? Can we render the basic units of soft oxometalates or the oxometalates or the polyoxometalates photoactive? Because our overarching focus is really now light and water. So, we have it in water, and then what we did is we designed a polyoxometalate that is a phosphotungstate, and as its counter ion, this time we designed it a little bit, we chose butyl methyl imidazolium. Now, why we chose it? We chose it because we could generate imidazolium. Now, this imidazolium radical cation provides us with two options. Number one, cationic polymerization. Number two, free radical polymerization. So, these are the two options that we can have using these material, using this counter ion. And as you can see, of course, here the conversion was not very high, it was around 40%, but the recovery was the conversion was not very high, it was around 40%, and the recovery was also reasonably okay, around 60 to 40%. And this was a method, and how we get it? We could only get it with this butyl methyl imidazolium cage. What we think is happening is that as you have the oligomers that are being formed, they are stabilized in this cage. If we get rid of this cage, if it's not there, then we don't get any polymerization. So, this is our first step towards light and polymerization, which I will come back to you later again in another system, but this is how we started building it up. Now, the next step what we thought is these were simple polymers, right? That means we were getting gels and things like that. Can we make polystyrene latex for example with this? And this is how we did it. So, what we did is we started with the same oxometalate. This time we added a little bit of DMSO so that we have a biphasic system and we can generate these soft oxometalate vesicles. So, that means we have a confined reaction chamber, so to speak. Now, within these soft oxometalate vesicles, we transported or we captured styrene. So, the styrene goes within the oxometalate vesicle, the SOM, and then we irradiate it with UV. Now, as we irradiate it with UV, if you remember from the last slide, these units that are on the surface gets to the excited state, photoexcited state. And then what they do is they polymerize the inner content. Now, you have a situation where you have a hydrophobic core and a hydrophilic oxometalate shell. They do not like each other, so they phase separate. You have a macroscopic phase separation, and then you can recover this, but this one then is in reduced state. So, you put it in air, you get it back in the initial state. What we can also do, now you will say, okay, what is the big deal? What is the big deal is that what we can also do, we can control the size of this vesicle by simply changing the dielectric constant. So, we can change the dielectric constant and we can make it smaller or larger. So, in this way we could make polystyrene spheres of controlled size. And I will go a bit more in detail. So you see, this is how it is happening. So this is, for instance, the cryotime image of the SOM vesicle, and this is the EDX. Now, because it is a vesicle with water in it, so as we probe it with the microscopic beam, with the electronic beam, it undergoes a deformation. But after some time, when it is polymerized, this is not very visible, but for instance, if you look at it, so it has an inner shell, and the polymer shell, as it goes on with time, the polymer shells gets thicker and thicker, then it does not suffer that beam damage. So that means it starts getting stabilized. And finally, we see this oxometalate ripping off the surface. This is the hydrophilic part, and this is the central hydrophobic polymer core. And finally, we have this polystyrene coming up. This is the transition state, or the intermediate state we could see. And you see all the bands that are present of polystyrene as well as the oxometalate. And what we see at the end is the macroscopic phase separation. This is the blue one. This is the reduced oxometalate that comes off from the dispersion, and you have the polystyrene. And you see here also the kinetics is sigmoidal. So which means that we have a heterogeneous catalysis, so which is characterized by the sigmoidal kinetics. And you have a conversion here also is a little bit low, but here you see the recovery is high, but it is fluctuating recovery, which is typical of heterogeneous catalysis. So what we have shown then is that you see a monodisperse polystyrene spheres of different sizes, simply controlled in each cycle by using light. There is no surfactant, no emulsifier, nothing. Only the soft oxometalate, and it's a clean system. You recover the soft oxometalate and you have a clean polymerization cycle. So you basically have a clean system with which, starting from 100 nanometers, you can go up to few microns, and we can go on and on. But the lower limit, if you look at it here, the intercept is around 40 nanometer. That means this is the lowest size up to which we can go. We cannot go below 40 nanometer, because that is the limiting size of the vesicle, below which we cannot get polymers. So having shown this, I would change gears and I would show you shape transition in the soft oxometalates. So what we mean by the shape transitions and why we are doing it. We are actually doing these shape transitions so as to induce, for instance, the transition states in catalysis, so as to make the transition states in catalysis that can be useful, so that we can induce shape changes and thereby provide a better fit for different catalytic reactions. I will not talk about those reactions which we are doing now. Like for example, we are doing, it's a little bit more organic, like triazine synthesis and click chemistry and things like that. I will not talk about it, but what I will talk about are the light induced phase transitions. So here we again start with this type of SOM. This is a molybdenum 7 based SOM. We shine light on it. Now this, if you look at the structure of the unit, this has a hexagonal symmetry. It's a C6 type unit. Now when we shine light on it, we generate this type of circular ring like structures, which provides us with a C5 unit and thereby induces a surface defect on the linear rods, and we get this type of spherocylindrical species. And then with longer irradiation time, we start getting these type of spherical species, which becomes blue because of the presence of MO5, MO6 intervalence charge transfer transitions. So they get blue. And then if you again take them up, open the cork, put them in air, open air, no heating, nothing, you again start oxidizing these ones, these loose shape, spherical shape, and get back to the linear shape. And in this way, we can go on and on cyclically. What we are doing now is using these intermediate steps and doing catalysis. That is what we are doing now, because a better fit induces better reactivity and better catalytic power. We have also checked it with electron absorption spectroscopy and of course with dynamic light scattering, that you can run this type of topological transformations in cycles, again in a water based systems using lights. Now I will talk about the phase transitions or the shape transitions or phase transitions or the crystallization in these soft oxometalates. This has been a work that I have been doing together with Oyon and with Malla Reddy and with Benthang. So, I will be talking, but primarily with Oyon. You see he is in both these things. So, what we did was the following. We started with a soft oxometalate dispersion. Now, when we start with the soft oxometalate dispersion, we shine light on it. Now, these oxometalates have a ligand metal charge transition band around 1064 nanometer. Now, when we talked, we proposed or we thought that can we tune the laser frequency to that, and luckily Oyon had that laser frequency. So, when we take this dispersion in the sample chamber, we shine laser onto it, and when we shine laser onto it, then what we see is that we have a bubble formation, basically a soft oxometalate bubble formation. So, what we see is that the oxometalate absorbs the laser intensity and forms a bubble. Now, this bubble grows with the irradiation time, and this kinetics almost follows like an Ostwald ripening. So, basically the radius of the growth of the bubble with that of the time, if you take log of both, then they follow a slope of around 1/3. Now, what happens is that with time this bubble grows. Now, you have or we have generated a temperature gradient, because here you have very high temperature and here you have relatively lower temperature. That induces a surface tension difference, and that in turn induces a Marangoni-Gibbs type convection current. So, you have more SOM particles that come from the bulk to the base of the bubble, and we see here, if we do Raman spectroscopy, a clear phase transition. So, here you have it for the tubes, but here you have it for the crystals. Now, if we move the sample chamber, or in other words, if we move the laser, but we are indeed moving the sample chamber, then we, instead of generating another bubble, this bubble moves, and the crystalline polyoxometalates that remain on the glass slide. So, in this way we could write patterns following our wish, and we wrote the name of our institute in this fashion, right. And Oyon will talk more a bit in detail about this phenomenology. And what we are able to do, we are also able to put other substrates like carbon nanotubes and make patterns like this. We were able to put glycine, we were able to put perylene, for example, to render it fluorescent and things like that. So, this was very attractive, this was very interesting for us. We thought, okay, fine, we can make patterns, but what next? Because of course, we were looking then for applications. So, then I moved on to the next step. So, with our friend in China, Benthang, and with my friend in India, Oyon, so we thought of taking the next step. Now, we thought that, okay, we have these soft oxometalates. These are nothing but colloids. Now, you have a possibility of putting in a polymer and having a polymer colloid type supramolecular composite. Now, if you are familiar, the choice was prompted by the existence of a molecular unit known as the phosphomolybdate Kegin, PMO12. It has both molybdenum and it has both phosphorus. So, we chose this phosphonium scaffold, phosphonium containing polymer, tetraphenyl phosphonium from Thangben, and we put into this molybdate so as to make a soft oxometalate porous organic framework composite. Now, this porous organic framework has high volume. So, that means you have lot of internal available volume where you can do the catalysis, and that is why we chose this, and we characterized this of course in the dispersion mode with highly attenuated total internal reflection, and we measured the zeta, and we see that we are in a we get an unstable regime, but we can move on to the stable regime which changes back into the unstable regime. So, we chose the stable regime, and then we decided, okay, fine, now can we make patterns out of it. So, we did the patterns, we wrote the patterns, we scraped out from the pattern, and we saw indeed on the very nanoscopic scale we have a phosphomolybdate supramolecular composite. So, that means we can do catalysis with it, and that is what we did. So, what we did is we did a simple reaction, benzaldehyde to benzoic acid, and we catalyzed it using this type of dispersion as well as the pattern chip. Now, on the pattern chip, when we do it, on the dispersion when we do it, we get a sigmoidal type curve. That means it is a heterogeneous type catalysis, right? And then we looked at the phase transition. For example, you can see from Raman spectroscopy, of course, you have a similar kind of phase transition, which is marked by the shifts in the Raman bands. In the micropore regime, we see the micropores are blocked here, and you have only the mesopores that are still available, and that means we have still the mesopores available for the reaction, and we believe that the reaction takes place in this mesoporic regime. And if you see at the thermogravimetric profile, the SOMPOF composite is much more stable than each of the individual component. And when we do this catalysis, what we see is that if we do it on the chip, we have a catalytic behavior, but that is on here, but if we do it here, we do not have any catalysis. So that means we have a site specific catalysis, which is quite interesting, and that means we can control the site where we can do the catalysis with these type of materials. So now we merged back the capacity, or we are doing this now with ion again. We merged back the capacity of polymerization with the patterning in the soft oxometalates, and this time, if you remember, we showed that we are able to make polystyrene. So this time we made a more useful one, the conducting polymers. We chose pyrrole, and we made these patterns, and you see these are like coil type of structures, clearly visible on the ACM. In the Raman spectroscopy, it also seems that we have this material. This is the red one is in the SOM, and the one is with the polypyrrole is the one with the SOM and the polypyrrole. And we see a conductance behavior change in the conductance with the loading of the SOM. So which means that the SOM acts as a Lewis acid, and it acts as a dopant, and it can induce a change in the conductive profile or in the conductivity profile of this type of composite. So we are able to make a conducting trail with the soft oxometalate and the polyaniline. Now Shubro is involved in this work with ion together with my student Shontu. So we are now finalizing this work. So now I will come to the future directions, what we are taking and what we are following right now. So we thought, so this I would reiterate, for instance, this all started with my meeting with Ronojoy in Pondicherry, where he asked, for example, that can you render these systems active? Can you make these particles move with chemistry? And this is what we did. So the chemistry is very simple. I would request you to focus. So this is one of the soft oxometalate particle, and you see this is a TEM image. So it is a little bit looks like a pencil, where you have the front closed and the back side is open, where there is a possibility for the gas to evolve. And what we do, it's a simple redox chemistry. We have the SOMS with molybdenum in +6 state. We just reduce this molybdenum to +5 state, and in this course of reaction, we oxidize hydrazine to form nitrogen. So this is the chemistry. That's it. And what we see is the following. So you see this particle moving. You see this particle moving away. So from you. So and we can, and we can run it continuously. So you see, this is the particle. Oops. This is the particle, it is moving away. So that means we can do it continuously, and we could track the patterns. Okay, so this is not the one which we have sent for publication. So we have another system. I'm sorry for this. So we have another one. This is now we are working on it. Yeah, and then what we have is also collective modes. So basically we have a pattern of, so recently I saw in the National Academy of Science a picture of Acule by Wine-Levine. It reminded me very much of the units of the flocking behavior that we see in our SOMS as well. It's very, very similar. So what we see is basically a collective mode, and we see the entire assembly moving with the evolution of gas. And if you look carefully, we have bands formation in this corner as well. So we also see, for instance, the change in velocity, and the velocity is not the fastest one, but it's one of the fastest ones, one of the faster ones. It has a velocity of around, yes.
So, are you sure it's a bubble formation, because the object seems to be almost...
This one is not a bubble formation.
Okay.
This one is not a bubble formation. The bubble formation was the last one. Yeah, this is a completely different one. So yeah, this is completely different. This is not a bubble. So basically this is just a redox reaction where we have, yeah, where we have this MO6 going to MO5, and we have the nitrogen gas. This is not a bubble. Yeah, and yeah, so in this way we see this type of whole assembly or ensemble moving around, and with a velocity profile which looks like this. And with Ronojoy we are trying to model this behavior, what is the exact mapping or the physical model, what gives us this type of profile, because in the literature you will see this type of profile, but there are no clear evidences or no clear explanations for this type of profile. So he is doing with Obro, and he has helped us with this, and we are working on this to finalize this type of patterns. And these are the trace lines which you see, and the lifetime of these hydrazine based SOM active motors are rather long. They are at least few days stable, but the problem is if you continue over a longer period of time, the color changes, and the person who is responsible or who is taking this project very much further is in the audience, is Opabrita. So she is working on it, and we have the next system which actually we have, I'm sorry for that mistake. So yeah, this one is in under revision in new journal. So basically here we use another type of chemistry, but it is again the same redox chemistry. So where we have dithionide reducing to sulfur dioxide. So here the sulfur dioxide is the propelling gas, and here we see here the video is not that nice, so I would still play it, but you may not see it. So if you focus, this is the one, this is the particle, and this will move, but this is not really very much visible, so you need to trust us, and these are the tracking tracing lines. But I will still show you the video and request you to focus on this one. So let me see. Yeah, is this one moving away? Yeah. So, so this is really not very much visible. I don't have a better video, but that's my fault. But we have very good results. I have got much better videos. So anyway, you can look at this one. So this is showing the tracking lines or the tracer lines with which we can show that we have the movement of the single particles. Here we do not have collective dynamics. The reason why we do not have collective dynamics is because it turns extremely dark blue. So it's not possible to see it anymore. It becomes completely dark, and you cannot see anything under the microscope with these moving active particles. But what is interesting, how we explain it here, is the following: that if you start with the molybdenum 6, then you reduce it, you generate a molybdenum blue diffusion, you generate a molybdenum blue reaction front which diffuses, and with the evolution of sulfur dioxide. So in between the SOM surface and the moving reaction interface, there is a drift velocity created due to the difference in the chemical potential of the sulfur dioxide that is evolved, and that is how this drift velocity is being induced and these particles move on. So this is how we have explained it, but it's a very phenomenological, very qualitative description. We are now working with Ronojoy for the next one with the hydrazine to come up with a quantitative model to explain the behavior. So with this, I would like to show you something exciting, that is water oxidation and water reduction using these SOMS. So what we have done, for instance, we changed the metal center, and we have this manganese. Now why we took manganese? If you are familiar with photosynthesis a little bit, then you know that manganese is an important cofactor in the photosystem too. So it does this water splitting type of reactions. So that prompted us to take the manganese core, And what we have done is we take this manganese based cluster. What it does is that it gets into the oxidized state, it gets into the excited state with light, it splits water, generates oxygen, and then also in the reduced state, it similarly gets into the excited state and it splits water to generate hydrogen and hydroxyl radical. And these are the SOM vesicles that we see here. So, for example, these are the microscopic image, and we think that they form these type of vesicular structures because of the layer lattice like formation which looks a little bit, resembles a little bit like graphene. So, you have like layers, so you have like two-dimensional layers. Of course, because of the free energy cost, they do not want to be floating around as free layers, but they buckle up, they curl up, and they form these vesicles. So, that is what we have, and because of this SOM vesicle formation, we have very high turnover numbers. So, we have multiple catalyst sites and we can do a lot of active catalysis with this. So, this one, and this is for example showing with different loading the oxygen generation, which is not pretty bad, which is around 12 micromoles. Of course, we are not the world record holders, there are much higher ones. And this is with cyclic voltammetry showing that you indeed have it, and we have now checked it with GCMS, and this is showing that hydrogen evolution with cyclic voltammetry. So, now having shown that, this prompted us to think of the next step, that can we couple oxidation of water with reduction of carbon dioxide exactly as it is done in photosynthesis. And this is what we have done, and I will show you here. This is what we do. This is unpublished result. We have filed a patent on this. So, this is what we do. So, we have these type of SOMs. Now, here the SOM dispersed phase is a little bit more complex. It is not only a simple oxometalate. It is graphene with molybdenum 132 type charge stabilized clusters. We shine light onto them. It goes into the excited state. Now, when it is in the excited state, it splits basically a photon into a hole and an electron. Now, this hole splits water into oxygen, proton and electron. This proton and electrons are stored, that is what we think, in the cluster, and the electrons are being relayed by the graphene matrix to reduce carbon dioxide into formaldehyde and formic acid. It is a clean reaction. We can run it over cycles, and we have filed the patent now. So, we are working on the publication, and we have a series of systems going on with this line. And you see, for example, this is from the Raman spectroscopy. So, we have the RGO where it shows the D and the G bands, and you have the shifted D and the G bands along with the molybdenum complex, which shows its signature peaks here, and you have here MO132 that are immobilized or placed on the graphene surface in the SOM. And this is what we see. For instance, here is the reduction of carbon dioxide, and here you have the water oxidation simultaneously taking place, and the turnover number, the turnover number is rather high. It's around 2,750, which is relatively high turnover number. Now, to conclude, I would say that we are not only focused on applied, but we are also doing a little bit of more fundamental studies as well. So, we have looked up how these clusters, what we showed, are being formed. So, what we do is we take a dispersion, we look at the combinatorial explosion in the library. What we find are these pentagonal units and these dinuclear linkers, and this is a work in collaboration with T. Pradeep from IIT Madras, Josep Maria Poble and Carlos Bo from University of Tarragona in Spain. So, we are collaborating and we are finishing this one, we are communicating this one up. So, what we see is, for example, we have these pentagonal units and these binuclear linkers. Now, these pentagonal units and binuclear linkers are depleted from the combinatorial library as we go on with time, and then we monitor it with in situ Raman spectroscopy as well. And what we see is, for instance, initially we have this molybdenum 5 type species these are the simulated Raman spectra and these are the experimental Raman spectra, and they match completely fine. And we see that initially we have these pentagonal units, and these pentagonal units then combine with the binuclear linkers and thereby form this type of MO9, O9 type triangular species of this icosahedral cluster. Now, you know, in an icosahedron you have 20 triangular faces that tile the entire surface of this icosahedron. So, 20 of these triangular MO909 species then form the entire cluster, and that is how we are showing the formation of this entire oxometalate unit. So, with this I come to the conclusion of my talk. So, what I have tried to do in this span of time today is to explore what we mean by soft oxometalates. We have talked about soft oxometalates in catalysis, have shown shape changes, phase transitions in soft oxometalates, and then in future directions we have shown the active particles that could be made exploiting the soft oxometalates by using a simple redox chemistry, and have also explored the possibility of artificial photosynthesis and have shown you also how one of these clusters work. With this I conclude my talk. I thank you for being there and thank once more my organizing friends for having given me this chance to talk in front of this very diverse audience, and I would be honored to take your questions. Thank you very much. And sorry, this is my group and these are my collaborators. So, just a little bit, Shubho worked on this MO132 and on the artificial photosynthesis, also Soumitra. Shontu is working a little bit on the patterning. Preeti was involved with the patterning with Oyon students, Basudev. Opabrita, who is here in the audience, is working on the active particles. Dipti is working on, okay, Orchishmita and Dipti, they are working on catalytic reactions, and these are my postdocs, and he worked on topological transformations. These are the grants. Sorry, yeah, thank you.
Okay, any questions?
Yes.
I'm concerned about calling it photosynthesis, right? Because taking in carbon dioxide, releasing oxygen, but photosynthesis also involves making food.
Yes, 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 right, right.
SOMS are certainly not doing that.
Right, but you see the concept is basically similar. So, why we are calling it photosynthesis is following. That is a very good question. So, why we are calling it photosynthesis is following. In living systems, right, in the biosystem, in the ecosystem, the currency of energy is food. Of course, you are right, right? But in our human economic ecosystem, the currency of energy is an upstream product like carbon monoxide or like formic acid. Because if we have glucose, for example, we cannot run cars with glucose, right? But if we have carbon monoxide, we can in principle run cars with carbon monoxide. And if we have formic acid, we can use them in fuel cells to run cars or run industry. So, that is why we are calling it photosynthesis. Yeah.
Okay, so looks like there are no other questions. So anyway, let's thank Soumyajit once again for a nice introduction to SOMS, and the next speaker has disappeared. Just so I'm